Ancient engineers built machines that rival our modern world. These 25 technological innovations from our distant past eerily predicted the future, challenging everything you thought you knew about history and human ingenuity. By the end of this journey, you will see human progress not as a straight line, but as a tapestry of brilliant ideas that were often lost, only to be rediscovered centuries later. We will uncover a 2,000-year-old computer, explore a Roman concrete that repairs itself, and ask how a formula for a terrifying liquid fire could simply vanish. What does it mean for our own future if such profound knowledge can be so easily forgotten? A corroded lump of bronze and wood pulled from an ancient shipwreck held a secret that would rewrite history. For nearly 2,000 years it lay at the bottom of the sea, its intricate gears locked in silence. When it was finally recovered off the coast of Antikythera around the turn of the 20th century, no one could have guessed it was the most sophisticated scientific instrument of the ancient world. This was not a simple statue or piece of pottery, it was a machine. Researchers initially baffled by its complex internal structure would later call it the world's first analog computer. Through painstaking analysis, including decades of work by historians like Derek de Solla Price, the truth slowly emerged. This device could calculate the movements of the sun, the moon, and the planets. It predicted lunar and solar eclipses with remarkable precision. It even tracked the 4-year cycle of the ancient Olympic Games, linking celestial mechanics to human celebration. The mechanism was a portable cosmos, a universe of knowledge turned by hand with a simple crank. Its creation speaks of a civilization, the Hellenistic world, that had reached a stunning peak of engineering and astronomical understanding. Yet this knowledge did not pass forward. The technology was lost seemingly for more than a millennium. How could something so brilliant, so advanced, simply vanish from the human story? The silent gears of the Antikythera Mechanism ask us a profound question about the fragility of our own progress, and what brilliant ideas we too might leave behind for the sea to claim. That same whisper of forgotten genius echoes from a simple clay jar, unearthed from the sands of Mesopotamia. Inside this unassuming Parthian artifact, dated to around 200 years before the Common Era, rested a copper cylinder and an iron rod. To an archaeologist in the 1930s, it was a curious puzzle, but when researchers theorized it could be filled with an acidic liquid like vinegar or wine, the puzzle transformed into a profound mystery. The jar became a battery capable of generating a small but measurable electric current. Imagine the spark of realization that must have occurred the moment someone connected the pieces and saw a glimmer of ancient voltage. What was this power used for? The most compelling theory suggests electroplating, a method for coating a less precious metal like silver with a fine layer of gold. Other ideas point to a religious function, perhaps providing a tingling sensation during rituals, or even a very early medical application. The true purpose may be lost to time, but the object itself is undeniable. It stands as a physical question mark, challenging our timeline of discovery. The formal principles of electrochemistry would not be laid down until the work of scientists like Volta in the 18th century, nearly 2,000 years later. So how do we explain this 2,000-year-old anomaly? Its existence suggests that the ancient world was a place of widespread experimentation, where the boundaries of natural knowledge were constantly being tested. This was not a one-off miracle, but likely a reflection of a broader, more curious technological landscape. The Baghdad Battery forces us to ask a difficult question. If they understood this basic principle of electricity, what other experiments were conducted, and how much of that practical knowledge simply faded away without a written record. It is a quiet, potent reminder that the spark of innovation can flare up in unexpected times and places, only to be dimmed by the passage of centuries. From the silent spark of a forgotten battery, we turn to a weapon of roaring, unstoppable fire. The Byzantine Empire possessed a secret so potent it could decide the fate of empires upon the waves. They called it Greek fire, a liquid flame that did not just burn but clung to the water itself, creating an inferno that could consume entire fleets. Imagine the terror of an opposing sailor watching a stream of fire arc from a Byzantine siphon, hitting the sea and only blazing more fiercely. Water, the one element that should offer salvation, became the very fuel for their destruction. This was not mere fire, it was alchemy made into a weapon. The exact recipe was a state secret of such immense value that its composition died with the empire that mastered it. Modern theories suggest a volatile cocktail of crude petroleum, perhaps mixed with quicklime, a substance that reacts violently with water to generate intense heat. This was chemical warfare on the ancient seas, a terrifying precursor to modern flamethrowers and incendiary weapons. Its strategic deployment required a deep, almost instinctual understanding of chemistry and physics, of pressure and propulsion. How could a formula so powerful, so central to the security of a civilization, simply vanish from human knowledge? The answer lies in the nature of secrets themselves and the fragile chain of masters and apprentices who carried them. When Constantinople finally fell, that chain was broken forever, leaving only legends and the haunting question of what other advanced chemical understandings were lost in the smoke of fallen cities. This mastery over fire leads us naturally to another elemental challenge, one that required an equally brilliant innovation: the mastery of water itself. While we grapple with the loss of Greek fire's volatile chemistry, another Roman innovation presents the opposite mystery, a formula so successful its results are still standing. The Pantheon's vast dome, the massive harbors at Caesarea, these are not ruins in the traditional sense. They are functional monuments, having weathered 2,000 years of storms, tides, and earthquakes. Modern concrete, by stark contrast, often begins to degrade within decades, especially in harsh marine environments. The Romans built for eternity, and they did it with a seemingly simple mixture of lime, volcanic ash, and seawater. The magic happened deep within this blend, where a slow chemical reaction with saltwater created rare, crystalline minerals like aluminous tobermorite. These tiny, interlocking plates act as a permanent reinforcement, actually blocking the spread of microcracks. When a small fracture does form, unreacted lime in the mixture dissolves and recrystallizes, effectively healing the wound. It is a material with a built-in immune system, growing stronger with age where modern concrete grows weaker. Today, material scientists are peering into the atomic structure of Roman harbor samples, desperately trying to reverse engineer this self-healing property. The goal is to create a new generation of concrete that could make our seawalls, bridges, and nuclear containment vessels vastly more durable and sustainable. The Romans arrived at this brilliant recipe not through advanced molecular theory, but through centuries of meticulous observation and practical experimentation. They saw what worked in the real world and refined it. This empirical mastery over their environment speaks to a systematic approach to engineering that extended far beyond mere mortar and stone, leading to equally ambitious projects for controlling the world around them. Hero of Alexandria's workshop must have been a place of pure wonder. In the 1st century of the Common Era, this brilliant mind described a device he called an eolipile, a simple but profound invention. A sealed sphere mounted on a boiler would shoot out jets of steam from two bent tubes, causing the entire sphere to spin with startling force and speed. This was not merely a curiosity, it was the world's first recorded steam engine, operating on the very principles of thrust and reaction that would one day propel jet aircraft and rockets into the sky. Yet for all its mechanical elegance, the Aeolipile was never used to grind grain or power a ship. It remained a temple wonder, a fascinating demonstration of power meant to inspire awe rather than to drive industry. Hero's other creations were equally visionary, from automated temple doors that seemed to open by magic to mechanical puppets that performed entire plays. His work reveals a culture steeped in mechanical experimentation, one that clearly understood the potential of steam and compressed air, so we are left with a haunting historical crossroads. The fundamental technology for a steam-powered revolution existed 2,000 years ago. Why did it not happen? The answer lies not in a lack of ingenuity, but in the social and economic landscape of the ancient world. Without a pressing need to replace widespread human and animal labor, without the financial systems and markets to drive mass production, the steam engine remained a magnificent toy. Its potential lay dormant, a spark that never found the kindling to start a fire. This question of how a society chooses to harness power or leaves it untapped finds a fascinating parallel in how ancient civilizations managed another critical resource, not steam but water, and built entire cities around its intelligent control. Buried deep beneath the sun-baked bricks of Mohenjo-Daro lies a network of baked clay pipes that tells a revolutionary story. In a city flourishing over 4,000 years ago, individual houses featured bathing areas and toilets, with waste channeled through a sophisticated system of covered drains that ran along the streets. This was not a privilege for the elite. It was a foundational principle of urban design for the entire Indus Valley civilization. They engineered the world's first known urban sanitation system, a complex web of hydraulics and civic planning with a single clear purpose: to protect public health. This was a society that understood, on a massive scale, the vital connection between cleanliness, water management, and the well-being of its people. Centuries later and a continent away, the Romans would elevate this concept to an even grander scale with their monumental aqueducts and the great sewer known as the Cloaca Maxima. These were not mere tunnels, they were the circulatory system of a vast empire, bringing fresh water into bustling cities and carrying waste away, enabling population densities that would not be seen again in Europe for over 1,000 years. The engineering prowess required to maintain a consistent water flow over such vast distances reveals a mastery of gravity and hydraulics that is still admired today. So how is it possible that such a fundamental, life-saving idea as city-wide sanitation could be forgotten? The intricate sewers of Mohenjo-Daro were eventually buried by dust and time, while the knowledge that built the Roman aqueducts fragmented in the wake of societal collapse. For centuries, many European cities would regress, with waste management becoming a disorganized and hazardous affair, leading to cycles of illness that the ancients had worked so hard to prevent. The loss was not of a single invention, but of an entire philosophy, the core understanding that a civilization's health is directly tied to its control over water. This ancient drive to command water resources did not stop at the city limits. It extended out into the arid landscape, where another civilization was performing miracles of hydraulic engineering to feed its people. Deep beneath the scorching desert sands, ancient Persian engineers solved a problem of survival with breathtaking elegance. They created the Qanat, a subterranean highway for water that transformed barren lands into blooming oases. The method was as simple as it was brilliant. Workers first dug a deep mother well, tunneling down to reach a hidden aquifer. From the base of this well, they then carefully constructed a gently sloping underground channel, just enough of a decline for gravity to pull the water along its course. This tunnel would stretch for miles, sometimes dozens of miles, with vertical access shafts dug at regular intervals for construction and maintenance. The result was a constant, reliable flow of fresh water emerging at the surface far from its source, all without a single pump or moving part. This was more than just an irrigation ditch. It was the lifeblood of an entire civilization. The Qanat system allowed cities to rise and agriculture to flourish in some of the most arid environments on Earth. The true genius of the design lay in its sustainability. By keeping the water deep underground and shielded from the sun, the Qanat minimized evaporation to almost nothing, a critical advantage in a desert climate. It was a self-regulating system, one that provided a consistent supply regardless of the scorching heat above. This ancient technology is not a relic. In parts of Iran and Oman, Qanats have been in continuous operation for nearly 3,000 years, a stunning testament to their perfect design. They stand as a powerful precursor to our modern ideas about sustainable water management and conservation, especially in drought-prone regions. In an era of growing water scarcity, what profound lessons can we learn from these millennia-old tunnels? The Qanat represents a philosophy of working in harmony with the landscape, of using subtlety and intelligence rather than brute force to command a vital resource. This ancient mastery over the elements was not limited to channeling water across vast deserts. It also extended to a more abstract challenge, the precise measurement of the world itself, guiding explorers across trackless oceans with a technology that seemed to defy the very sea and sky. The Lighthouse of Alexandria did not merely stand, it presided over the sea, reaching a height that would rival a modern 30-story building. Its white marble form was a declaration of human ambition against the vastness of the ocean. This was far more than a tower with a flame. It was an intricate machine for light. At its summit, a massive mirror, likely a vast disk of polished bronze, captured the Mediterranean sun by day, directing a concentrated beam toward the horizon to guide ships. When darkness fell, a colossal fire was kindled, its light amplified and projected by that same mirror system, creating a beacon visible from an incredible distance out at sea. This was optical engineering on a colossal scale, a direct ancient ancestor to every modern lighthouse that guides vessels through treacherous waters. The very principle of focusing a light source for maximum range and clarity finds a parallel today in concentrated solar power plants, where mirrors focus sunlight to generate immense heat. The logistical genius extended to the structure itself. An internal ramp, wide and gently sloped, allowed a steady stream of workers or donkeys to carry bundles of wood and fuel to the summit, a continuous supply chain operating inside the monument. For over 16 centuries, it served as a universal symbol of safety and a testament to a society's commitment to public works and maritime commerce. Its design and purpose became the archetype for coastal navigation aids for millennia to follow. How did mariners, once guided by such a grand beacon, then find their way when they sailed beyond the sight of land, venturing into the open ocean where no lighthouse could reach? A polished brass disc, etched with a delicate web of lines and curves, could hold the very sky in the palm of your hand. This was the Astrolabe, the smartphone of the Middle Ages, a device of breathtaking elegance and utility. For over 1,000 years, it was the essential tool for anyone who needed to measure the heavens, from sailors navigating by the stars to astronomers charting the planets or timekeepers marking the hours of prayer. Its invention is credited to the brilliant minds of the Hellenistic world, but it was Islamic scholars and craftsmen who refined it to its peak, engraving their intricate designs and precise calculations onto its shimmering surface. To use an astrolabe was to hold a portable model of the universe. You would suspend it by a ring, allowing a sighting bar called an alidade to rotate and measure the altitude of a star or the sun. Then, by turning the device's main disk and its pierced, rotating plates, you could solve dozens of practical problems. It could tell you the time of day or night, predict the rising and setting of celestial bodies, and even determine your latitude on the Earth's surface. This was not a passive map, it was an interactive computer, an analog processor that translated the complex movements of the cosmos into actionable, earthly information. The true legacy of the astrolabe, however, is not just its mechanical genius, but the story of knowledge it carries across cultures. Its design journeyed from ancient Greece through the heart of the Islamic world, where it was enhanced with new scales and projections before passing into medieval Europe. This was not a secret held by one civilization, but an idea that grew richer with every hand that held it. Its fundamental principles of celestial mapping directly paved the way for more precise instruments like the sextant, which would one day guide European explorers across the globe. So what does this journey tell us? It reveals that scientific progress has always been a collaborative, cross-cultural endeavor. The evolution of the astrolabe stands as a powerful testament to the fact that human curiosity knows no borders, and that our greatest tools are often the product of many minds across many centuries, all looking up at the same stars. This drive to map the heavens finds a perfect parallel in an equally ancient human obsession, the desire to chart the world beneath our feet. A Roman scholar working in the great library of Alexandria laid out the entire known world on a grid. Claudius Ptolemy's Geographia was not merely a collection of maps, it was a set of precise mathematical instructions for creating them. He introduced a coordinate system of latitude and longitude, a concept so fundamental it remains the invisible skeleton of every digital map and GPS device you use today. His true genius, however, lay in confronting a problem that every cartographer still faces: how to accurately portray our spherical planet on a flat sheet of paper. Ptolemy developed several map projections, geometric methods for translating the curved lines of the Earth onto a two-dimensional surface. This was not just an academic exercise, it was a practical tool of immense power for the administration of a vast empire, for planning trade routes, and for conceptualizing distant lands. His work demonstrates that ancient scholars possessed a remarkably sophisticated understanding of the world's shape and size, and the mathematical tools to represent it systematically. But the survival of this knowledge through the following centuries is a story in itself. Ptolemy's Greek texts were preserved and enhanced by Islamic scholars, who translated and expanded upon his work, adding new observations and corrections before his ideas eventually filtered back into a rediscovering Europe during the Renaissance. How is it that the foundational logic for our modern global positioning systems was codified nearly 2,000 years ago? This ancient drive to measure and codify the world was not confined to geography. It found another profound expression in the very structure of human communication, where a different kind of code was being invented. A merchant in ancient Rome could calculate a complex bill of sale faster than you could pull out your phone. The tool that made this possible was not a secret or a mystery, but a simple frame strung with beads, the abacus. From the bustling markets of Mesopotamia to the administrative halls of China, and even in the sophisticated mathematics of the Maya, this device emerged independently across the globe. Its design was universal genius, a physical manifestation of the place value system long before such a concept was formally written down. Each rod represented a different order of magnitude, ones, tens, hundreds, and sliding the beads was a direct tactile way of adding and subtracting, of carrying over numbers and borrowing them. This was not just counting, it was computation. The user of an abacus was performing arithmetic at a speed that could rival a person using a modern electronic calculator for basic operations. It engaged the mind in a unique dance of hand and thought, building a powerful muscle memory for numerical logic. This process of moving beads to represent changing values is deeply analogous to the binary logic that drives every digital computer today, where circuits are either on or off, 1 or 0. The abacus was the world's first truly successful user interface for mathematics, a bridge between human intuition and mechanical calculation. It formed the computational backbone of commerce, taxation, and engineering for centuries, proving that the need for swift, reliable calculation is a universal human constant. What does it say about our own computational thinking that this ancient tool is still used in some classrooms today to teach children the fundamental concepts of number sense? The enduring power of the abacus lies in its elegant simplicity, a direct physical connection to the abstract world of mathematics. This drive to compute earthly numbers finds a fascinating parallel in humanity's ancient obsession with calculating the movements of the heavens themselves. 2,000 years before modern seismographs, a magnificent bronze vessel stood in a Chinese court, designed not to predict the future, but to listen to the Earth's deep and secret movements. In the year 132, the brilliant inventor Heng unveiled his Earth motion instrument, a device of staggering elegance and purpose. It was adorned with 8 dragons, each one poised over a bronze toad with an open mouth. Inside the vessel, a complex but clever mechanism remained perfectly balanced, waiting. When the faintest tremor from a distant earthquake rippled through the ground, the internal pendulum would swing, triggering a single dragon to release its bronze ball with a resonant clang into the waiting toad below. This was not magic, it was a masterful application of physics, an early inertial sensor that could pinpoint the direction of a quake's epicenter from hundreds of miles away. Historical records tell of an occasion when a ball dropped without any local shaking, and days later, messengers arrived from the indicated direction confirming a major earthquake. How could a device from the 2nd century achieve such sensitivity without any electronic components? The genius lay in its understanding of wave mechanics, detecting the primary waves that travel faster and arrive before the more destructive tremors. This was the world's first effective early warning system, a tangible effort to bring scientific measurement to the terrifying unpredictability of natural disasters. Zhang Heng's seismoscope represents a fundamental shift in thinking, moving from seeing earthquakes as acts of the gods to understanding them as physical phenomena that could be observed, measured, and understood. This same drive to measure the invisible forces of the world would soon turn inward, from the shifting ground beneath our feet to the intricate rhythms of the body itself. A 3,000-year-old wooden toe, discovered still attached to the foot of an Egyptian noblewoman, is more than an artifact. Its worn surface and carefully articulated design show it was not for show, it was for walking. This was a functional device, meticulously carved and refitted over time to restore balance and mobility to its wearer. The craftsmen who made it demonstrated a profound, practical understanding of the human body, shaping the wood to distribute weight and minimize discomfort during use. This blend of carpentry and early anatomy represents one of humanity's first steps into the field of biomechanics, a direct ancestor to the carbon fiber and microprocessor-controlled limbs of today. It speaks of a quiet, compassionate ingenuity, a drive to use available technology not for conquest or spectacle, but to mend a life and restore a fundamental human ability. What does this tell us about ancient values? It reveals that the desire for a full and functional life, the impulse to overcome physical hardship through innovation, is a timeless part of the human story. This ancient ingenuity applied to the human form did not stop with external aids. The same drive to understand and heal the body was also turning inward, developing tools for diagnosis that required listening to the body's most subtle whispers. The same precision that defined Roman water channels and astronomical devices was applied to the most delicate of tasks, the human body itself. In the shadow of Mount Vesuvius, the volcanic ash that entombed Pompeii preserved a medical legacy of startling sophistication. Archaeologists have uncovered entire sets of surgical instruments, their forms chillingly familiar. There are bronze scalpels with replaceable steel blades, finely toothed bone forceps for extracting fragments, and elaborate speculums designed for internal examinations. These were not general-purpose tools, but highly specialized instruments, each crafted for a specific and often complex procedure. A Roman surgeon possessed the means to perform cataract surgery, carefully displacing a clouded lens from the field of vision. They could skillfully set broken bones and even undertake trepanation, the meticulous drilling of a hole in the human skull, likely to relieve pressure from a head injury. The existence of such a toolkit implies a deep, systematic understanding of human anatomy, gained not just from theory but from hands-on practice. This was a culture that believed in direct physical intervention to heal. But their advanced thinking extended far beyond the tools themselves. Roman medical texts advocate for practices we consider foundational to modern medicine. They understood the critical importance of cleaning wounds and sterilizing their instruments, often using boiling water or strong wine as antiseptic agents. They pioneered the use of natural opiates derived from plants like poppies to sedate patients, dulling the immense pain of these invasive procedures. This combination of precise engineering and empirical medical knowledge represents a peak of ancient medical technology. Yet, with the fragmentation of the Roman world, this systematic approach to surgery largely faded from Europe. The knowledge was not entirely lost, but was preserved and expanded upon in the Byzantine Empire and the Islamic world, where scholars translated and commented on Roman medical texts. It was through these channels that this forgotten expertise eventually filtered back into Europe during the Renaissance, inspiring a new generation of anatomists and surgeons to rediscover the principles of their ancient predecessors. How is it possible that the blueprint for a modern surgical toolkit existed 2,000 years ago, only to be misplaced for centuries? The answer lies in the fragile nature of specialized knowledge, which can vanish when the institutions that support it collapse. This obsession with precision, so evident in the surgeon's scalpel, found another profound expression in the ancient world's relentless pursuit of measuring time itself. The steady drip of water marked the hours long before the tick of a clock. In the ancient world, the clepsydra, or water clock, transformed something as fluid as time into a measurable, manageable resource. From the sun-baked courts of Babylon to the philosophical schools of Greece, these devices provided a constant, reliable measure of the hours, independent of the sun or stars. At its heart, the principle was elegantly simple. A container would either fill with or drain of water at a carefully regulated rate, and a scale along its side would translate the changing water level into the passage of time. But this basic concept could be engineered into something truly spectacular. In Alexandria, the inventor Ctesibius created a water clock of breathtaking complexity. His design incorporated a sophisticated system of gears and floats, powering automata that would strike bells on the hour or parade miniature figures in a mechanical theater. This was not just a timekeeper, it was a public spectacle, a symbol of a society's mastery over the natural world. The need for such precision was driven by the intricate machinery of civilization itself. A clepsydra regulated the night watch in military camps, ensuring sentries changed at their posts. It timed the speeches of orators in Athenian courts, granting each side an equal measure for their arguments. For early scientists, it provided the consistent intervals necessary to conduct repeatable experiments, laying the groundwork for the empirical method. The legacy of the water clock flows directly into the oscillating quartz crystals and atomic vibrations that govern our modern timepieces. Both rely on a constant, repeating natural process to segment eternity into usable pieces. This ancient drive to quantify time reveals a profound truth that the coordination of human endeavor on a grand scale, from law to science to commerce, demanded a shared, objective measure of time's passage. How many other facets of our modern world were first given structure by the relentless, quiet drip of a water clock? This mastery over measured intervals soon found expression in another domain, where timing was not about hours, but about the precise sequence of events in a grand and dramatic spectacle. A simple spiral inside a tube conquered one of humanity's oldest challenges, the need to move water uphill. Attributed to the brilliant mind of Archimedes in the 3rd century before the Common Era, this device is a marvel of elegant physics. A large screw sits snugly within a cylindrical housing, and when a person turns the handle at its base, the rotating spiral effectively scoops up water from a lower source, carrying it steadily upward along the threads until it pours out from the top. The sheer genius of this design lies in its continuous action, a constant flow achieved with a simple, repetitive motion. It was a revolutionary tool for its time, deployed to irrigate thirsty fields, to drain flooded mines of their seepage, and even to bail out the bilge water from the holds of ships. Can you picture the profound impact this must have had? It allowed societies to farm land previously considered too dry, to extract mineral resources from deep underground, and to travel greater distances by sea. The most astonishing part of this story is that the fundamental design of the Archimedes screw has not been improved upon in over 2,000 years. You can find modern versions, now often powered by electric motors, actively moving water in agricultural settings and even in wastewater treatment plants, handling materials far more challenging than clean water. Its enduring success is a testament to its perfect application of a basic mechanical principle, the inclined plane, wrapped into a continuous spiral. This device did not just move water, it lifted the very potential of human civilization. Why has this simple machine remained virtually unchanged for so long? Because it represents a kind of technological perfection, where the solution is so perfectly matched to the problem that no alteration is necessary. This ancient mastery over the physical world, using simple motion to command a fundamental element, would soon find a parallel in the way other cultures learned to harness an even more powerful and invisible force. While the Archimedes screw mastered the flow of water, another civilization learned to command the very air. In the windswept plains of ancient Persia around the 7th century, engineers constructed towers of stone and clay with a remarkable secret inside. These were not defensive structures, but the world's first documented windmills. Their design was a stroke of genius, featuring a vertical central shaft with sails made from bundled reeds or cloth. When the relentless desert winds blew, they caught these sails, spinning the entire apparatus around its central axis to power a grindstone for grain or a pump for water. This was not a small-scale experiment. It was one of humanity's first large-scale uses of renewable energy. These mills allowed communities to flourish in arid landscapes by automating the most labor-intensive tasks, turning the grinding of flour from a day-long chore into a continuous mechanical process. The Persian windmill is a direct and elegant ancestor to the vast fields of horizontal axis wind turbines we see today, both capturing the wind's boundless energy to do essential work. How did this brilliant Persian technology spread and evolve as it moved westward? The knowledge traveled along trade routes, reaching the Middle East and eventually Europe. There, engineers adapted the design, creating the iconic horizontal windmills with 4 large sails that became a classic feature of the European countryside. This evolution demonstrates a continuous thread of innovation, where a core idea is refined across cultures and centuries. The development of the windmill marks a pivotal moment in our relationship with nature, an early recognition that we could harness immense, impersonal forces beyond human or animal muscle. It speaks to a cleverness in designing machinery that works in harmony with the environment, a principle that feels profoundly modern as we again turn to the winds to power our world. This ancient mastery over natural forces extended beyond harnessing the wind and water. It was also reflected in the very materials they created and the objects they shaped with stunning precision. The shimmering surface of a Damascus steel blade held a universe within its rippling patterns. Forged from ingots of Indian wood steel, these were not mere weapons but masterpieces of molecular engineering. The process began in a sealed crucible where iron was melted with precise amounts of carbon-rich materials, then cooled with agonizing slowness over days. This meticulous thermal cycling did more than temper the metal. It triggered a transformation at a level invisible to the ancient smiths. Within the steel, microscopic structures self-assembled into carbon nanotubes, threads of carbon atoms arranged in perfect crystalline lattices that reinforced the blade with a strength and flexibility that seemed almost supernatural. A sword made from this material could reportedly slice through a silk scarf as it fell through the air, its edge remaining lethally sharp through brutal combat. The true marvel is that this nanotechnology was achieved entirely through empirical skill, through generations of artisans who mastered a recipe without understanding the atomic dance they were directing. How could such a profound material science breakthrough simply fade from memory? The knowledge was a closely guarded secret, passed from master to apprentice in a fragile chain that was ultimately broken, perhaps by political upheaval or the disruption of trade routes that supplied the unique raw materials. By the 18th century, the method was lost, leaving behind only the legendary blades and their mesmerizing, watery patterns. Today, materials scientists study these ancient artifacts with advanced electron microscopes, not just to unravel the historical mystery, but to learn from them. The spontaneous formation of carbon nanotubes in Damascus steel offers clues for creating stronger, lighter, and more resilient modern alloys. This ancient quest for the perfect weapon inadvertently forged a path toward the advanced materials of our own time, proving that the drive for superior defense has always been a powerful engine for innovation, a theme echoed in the very architecture created to withstand attack. A soldier standing on a city wall could unleash a storm of bolts without ever lowering his weapon. The Chu-Ko Nu, or repeating crossbow, transformed a single defender into a one-person volley. Its brilliance was not in raw power but in relentless mechanical rhythm. A wooden magazine sat atop the weapon, gravity feeding a succession of bolts into the firing track. All the operator had to do was work a simple lever back and forth, a motion that drew the string, released a bolt, and reset the mechanism in one fluid, continuous cycle. This was the assault rifle of the ancient world, a weapon designed for sheer volume of fire. Its effectiveness was not measured in the distance it could travel, but in the wall of projectiles it could create in a short, brutal span of time. Imagine defending a fortress gate against an advancing force, only to be met by a constant, chattering hail of fire from a single position. The tactical advantage was immense, allowing a smaller defending force to hold a position against overwhelming numbers. This was not a weapon of the open field, but of choke points and fortified walls, where its limitations in range and penetration were outweighed by its ability to deny an area completely. How did this early automation change the very nature of combat? It introduced a new variable, the concept of suppressing fire, where the constant threat of projectiles could pin down opponents and break their momentum. The mechanical principles at work, a clever orchestration of levers, springs, and gravity, represent a fundamental step toward the automated weapons that would follow centuries later. The simple, reciprocating action of its lever is a direct mechanical ancestor to the cycling bolt of a machine gun. This drive to increase the rate of projectile fire naturally spurred an equal and opposite reaction, a relentless innovation in the art of personal protection. Beneath the marble floors of a Roman villa, a quiet fire was the heart of the entire home. This was the Hypocaust, an invisible network of warmth that transformed living spaces through a simple but brilliant principle. A furnace constantly tended by servants would heat air to a tremendous temperature. Instead of letting that heat escape, architects channeled it through a void beneath the floor, which was raised on countless short pillars of brick or stone. The hot air would then circulate through hollow tubes built right into the walls before finally escaping through carefully placed roof tiles. The entire structure, from the floor you walked on to the walls around you, became a single, radiant heating panel. This was not just a fireplace in a room, it was central heating for the entire building, a concept of comfort that would not become common again in Europe for over 1,000 years. The engineering required a deep, intuitive grasp of thermodynamics and airflow, ensuring heat was distributed evenly without creating dangerous hotspots that could lead to fires or structural damage. This system powered the legendary Roman baths, turning vast public spaces into warm, social havens even in the depths of winter. But its presence in a private villa speaks to more than just technical skill. It reveals the stark social and economic divides of the ancient world. The Hypocaust was a luxury of immense cost, requiring not only specialized construction but a constant supply of fuel and dedicated labor to maintain the furnace. It was a tangible symbol of wealth, a way to physically separate the comfort of the elite from the chill experienced by the common citizen. How is it that such a fundamental idea for controlling our indoor environment could be lost and then independently reinvented so much later? The answer lies in the collapse of the complex economic and social structures that made such lavish, energy-intensive comfort possible. This mastery over the built environment, this desire to shape the very space we inhabit for both grandeur and comfort, found its ultimate expression in another Roman innovation, one that would define their architectural legacy for millennia. A Maya astronomer could predict the cycle of Venus with an error of just 2 hours over 500 years. This staggering precision was not magic, but the result of relentless observation, generation after generation, studying the night sky from stone observatories high above the jungle. Their entire conception of time was built on interlocking cycles, a cosmic clockwork of breathtaking complexity. The Hob was a 365-day solar calendar that tracked the seasons with near-perfect accuracy, superior to the calendar used in Rome at the very same time. Yet this was just one gear in a much larger machine. The sacred Tzolk'in cycle of 260 days meshed with the Hob to create the 52-year calendar round. And overseeing it all was the long count, a linear chronology that measured time in grand, sprawling epochs, allowing them to place any event within a vast historical framework stretching back thousands of years. This entire temporal architecture rested on a mathematical foundation that was centuries ahead of its time, for the Maya were one of the very first civilizations in the world to grasp and actively use the concept of zero, a placeholder that gave their numerical system immense power. How did a culture without telescopes achieve such celestial insight? They turned their cities into instruments. Pyramids and temples were precisely aligned to capture the sun's light on the solstices and equinoxes, casting specific shadows that marked the passage of the year with stone and shadow. Windows in observatory towers were positioned to frame the extreme risings and settings of Venus, a planet they associated with war and divine authority. Their cosmology was not separate from their daily life. It was the very fabric of it, driving this relentless pursuit of order in the cosmos. This celestial precision is perfectly mirrored by the Mayas' terrestrial achievements in writing and record-keeping, where they carved their understanding of time and the gods into stone for the ages. High in the Andes, a messenger could run the entire length of an empire without ever leaving a paved road. The Inca road system was a web of stone and ingenuity stretching over 40,000 kilometers, a distance that could nearly circle the entire planet. This was not a single path but a complex network of two parallel main highways, one along the coast and one through the soaring mountains, linked by countless smaller roads that reached into every valley and settlement. Engineers built stairways directly into cliff faces, carved tunnels through solid rock, and laid stone pavements that have endured for more than 5 centuries. But the most breathtaking crossings were the suspension bridges, woven from native grasses into cables as thick as a person's body. These organic structures swung precariously over roaring Andean gorges, yet they were so strong they could support the procession of a royal litter or the movement of an entire army. How could a civilization without the wheel, without iron tools, without even a written language as we know it, achieve such a monumental feat of engineering? The answer lies in a profound understanding of their environment and an unparalleled system of labor organization. The Inca did not conquer their landscape, they collaborated with it, using local materials and knowledge to build an infrastructure that moved people, goods, and information with stunning efficiency. A network of relay runners known as chasquis could carry a message or a parcel of fresh fish from the coast to the highland capital of Cuzco in a matter of days, a communication system that rivaled the speed of anything in the world at that time. This logistical mastery was the true backbone of their power, allowing them to administer a vast and diverse empire from a single center. The constant flow of messengers, soldiers, and traders along these routes bound the empire together, functioning as the ancient equivalent of a modern interstate highway system, complete with rest stops and storage depots placed at strategic intervals. What does it say about a society that invested so heavily in connection? It reveals that the greatest power in the ancient world was not held by the sword alone, but by the road, the bridge, and the runner who tied a continent together. This incredible network for moving physical things so efficiently finds a fascinating parallel in the ways other ancient cultures sought to preserve something far more intangible, the very thoughts and knowledge of a civilization. A single clay disc unearthed in the ruins of the Minoan palace of Phaistos holds a silent conversation that no one living can understand. Dating to the 2nd millennium before the Common Era, its surface is a captivating spiral of 45 distinct symbols, from marching men and helmeted heads to bees and ships, all perfectly stamped into the clay. This is the Phaistos disc, and its mystery is twofold. First, no one has ever cracked its code. The sequence of symbols spiraling inward could be a hymn, a law, a story, or a king's inventory, but its message is locked away forever. The second, even more profound mystery lies in its very creation. Each symbol was not carved by hand, but pressed into the soft clay using individual, pre-formed seals. This was movable type. A craftsman had a set of reusable stamps, each bearing a single sign, and arranged them in order to print this message, a technological concept that would not revolutionize the world for another 3,000 years with Gutenberg's press. So we are left with a breathtaking possibility. The idea of printing was born in the Bronze Age, a solitary spark of genius captured in this one-fired clay object. Yet no other example has ever been found, no other text, no workshop of stamps, no descendant technology. The Phaistos disk is a technological island, a brilliant idea that seemingly went nowhere. Its profound isolation forces us to reconsider how innovation truly spreads. An idea, no matter how brilliant, is not enough. It needs a society ready to adopt it, an economic reason to replicate it, and a way to transmit the knowledge across generations. Without that fertile ground, a revolution can be stillborn, its only evidence a single, beautiful, and utterly lonely artifact. What other revolutionary concepts captured in clay or stone have we simply never found? This question of unique, context-specific technologies finds a stunning answer not in a single object, but in the acoustic properties of an entire city. Surveying these 25 ancient wonders, a haunting pattern begins to emerge from the noise of history. It is the recurring story of knowledge itself, brilliant and yet heartbreakingly fragile. Civilizations would reach a dazzling peak of ingenuity, creating solutions to challenges we still face today, only to have that understanding vanish into the silence that followed their decline. The intricate gears of the Antikythera Mechanism, the terrifying formula for Greek fire, the self-healing recipe of Roman concrete, these are not isolated curiosities. They are evidence of dark ages, periods where complex technological understanding was erased, forcing humanity to relearn what it had already discovered. This challenges the comforting idea of progress as a straight, ever-upward line. Instead, it suggests that human knowledge is more like a garden, one that requires constant tending and nurturing. If it is neglected, if the gardeners change or the language of its care is forgotten, the most precious blooms can be lost for centuries, overgrown by the weeds of time. This historical fragility underscores a profound truth, that the mere existence of an idea is not enough. Its survival depends on robust, resilient systems for preservation, on the tireless work of translators, librarians, and teachers who transmit it across the chasms of generations and cultures. It makes you wonder, looking around at our own technologically saturated world, what are we taking for granted? Which of our own foundational technologies, from the global network of the Internet to the precise manufacture of a microchip, could one day become a mystery to our descendants, a legend of a golden age they can no longer replicate? The legacy of these ancient ideas is not just their cleverness, but the stark warning they carry about the permanence of our own achievements. The silent gears of the Antikythera Mechanism and the forgotten recipe for Roman concrete are more than museum pieces, they are active blueprints for the future. Today's material scientists peer into the atomic structure of ancient harbor samples, not as historians, but as engineers seeking answers to a modern crisis. Our own concrete infrastructure crumbles within decades, but the Roman version has endured for millennia, healing its own cracks. By deciphering this self-repairing chemistry, researchers aim to create a new generation of building materials that could make our bridges, sea walls, and even nuclear containment vessels vastly more durable and sustainable, dramatically reducing the environmental cost of constant repairs. This is not mere imitation, it is a conversation across centuries. Similarly, in a world facing growing water scarcity, the ancient Qanat system offers a masterclass in sustainable resource management. Modern engineers are revisiting these subterranean channels as a model for passive irrigation, a way to deliver water in arid regions without the massive energy consumption of electric pumps and with minimal loss to evaporation. The past, it turns out, is a vast and largely untapped repository of brilliant, time-tested ideas. The story of these anticipatory innovations teaches us a profound lesson about the nature of human ingenuity. Genius is not a linear progression. It is a capability that has flared with astonishing brightness across different eras and cultures. The next great technological breakthrough, whether in energy, materials, or urban design, might not only be found in a laboratory, but could be hidden in a forgotten manuscript or waiting within an unexcavated ruin. How can we better integrate this deep well of ancestral wisdom into our relentless push toward the future? Perhaps it requires a shift in perspective, to see archaeology not just as the study of what was, but as a vital source of inspiration for what could be. This synthesis of old and new thinking brings our exploration to a thoughtful close, leaving us with a powerful reminder that the most visionary path forward may sometimes begin with a careful look back. From the computational gears of the Antikythera Mechanism to the self-healing chemistry of Roman concrete, this journey through 25 ancient marvels paints a portrait of human history that is far more dynamic and brilliant than we often assume. These were not random flukes of genius, but the products of sustained inquiry, of cultures deeply engaged in observing their world and daring to experiment with its fundamental principles. They possessed a profound understanding of nature that, in countless ways, eerily predicted the technological landscape we inhabit today. These artifacts and ideas stand as a powerful reminder that the drive to innovate is a human constant, not a privilege reserved for our modern era. The line separating the ancient world from our own is not a solid wall, but a blurred and permeable boundary where the echoes of past ingenuity still resonate in our daily lives. Let this exploration be a call to see history with fresh eyes, to look upon the civilizations that came before us not as primitive, but as fellow travelers on the long and winding road of discovery. They faced their own challenges with the tools and knowledge they had, and their solutions continue to offer us wisdom and wonder. We would love to hear which of these ancient innovations most surprised or inspired you. Please share your thoughts in the comments below, and if you enjoyed this journey into the fascinating mysteries of our past, subscribe for more explorations that challenge everything you thought you